outside of AI and all of the topic we're talking about should be welcome. Let's avoid spamming the chat with links or advertisements or anything off topic. We have already joined on time, but also to get the full scope of this event, let's make sure to stay to the end. Feel free to ask your question or drop your section in the chat box, because there's going to be an opportunity to answer your question. And this is a great opportunity to learn and to connect. You can connect also, just connect with somebody in the community too. Most importantly, let's have fun, enjoy the session, and then make sure you keep the community engaged. So a quick rundown of how the session will run. We've already done the welcome and then the main session, which I'm soon going to hand over to Emmanuel. Then we're going to have a Q&A, and then we're going to have a little announcement and then wrap up. And then, yeah, this session is about 7 AI workloads in NVIDIA Dynamo, which is going to be hosted by Emmanuel Bashorun. I'm going to just quickly go through Emmanuel's bio. Emmanuel is a software engineer with over 5 years of experience in building software and infrastructure in the industry. These days, he spends most of his time exploring the frontiers of machine learning systems to build intelligence to chip to meter. His interests include inference and GPU, group performance optimization, Linux, and distribution system. I'm going to leave Emmanuel to maybe blow his own trumpet further. So Emmanuel, I'm going to stop showing and stop sharing, just in case you have your slide, so that you can have the floor full.
Thank you. So I will just go about sharing. Okay, so I'm sharing now, and hopefully everyone can see. If you can, just all right. Okay, sounds good. All right, thank you everybody, and thank you for the introduction. So today we'll be talking about 7 AI models on NVIDIA Dynamo, and this is sort of going to be like an extension, but at the same time we'll also try to go over what we talked about concerning NVIDIA Dynamo during our last session last year, December. And so that was when we had our first introduction to NVIDIA Dynamo. But then we didn't have enough time. So I think it's like a 30-minute session, right? So we didn't have enough time to go as deep as I thought we could, right? So this session would, like the aim of the session is to also talk about the things that we didn't, and then we'll also have some time to perform some demonstrations. I have like about 2 demos we're going to look into here to just have an intuitive grasp and understanding of what NVIDIA Dynamo tries to do. And then for people who are just joining, I think we'll probably have some people who are here that were not around during the last session on NVIDIA Dynamo. So we'll also go through what NVIDIA Dynamo is, the fundamentals of it, and like in order to bring everybody up to speed, then we proceed from there. So this just basically gives us a rundown of what we're touching on. Why Dynamo exists, high-level components, low-level aggregated 7 demonstration. We also have one for disaggregated 7, and then we'll talk a bit about meeting SLA requirements, and then a conclusion. A brief introduction. I think, do I just need to extend this? Well, a brief introduction about myself is I'm a software engineer, Linux, and cloud ops. Currently focusing on infrastructure tooling for ML systems. So the inference engines from the runtime's infrastructure layer, basically. So the inference engines that like power our models, and even down to building the actual components and the runtime. So Dynamo is one of them. Currently, I've most of my time goes into NVIDIA Group, which is used for topology hour scheduling. I will talk a bit about that too during the course of our session. My I always like saying is my clinical background is in the virtual sciences. I studied marine sciences from University of Lagos. Yeah, I enjoy hitting the gym. Um, by the way, do I need to extend this into a slideshow format, or this is okay? Something like this. Just let me know if you can. This is fine. All right, okay, sounds good. So we're going to talk about why Dynamo exists, and I want this to be as interactive as possible. So I will be I will do most of the talking, and I'll also do some demonstrations. But at the same time, I could maybe ask a bit of some questions just to keep maintain a bi-directional relationship between us ourselves. So first thing is, why does Dynamo exist? So Dynamo is basically a distributed infrastructure, right? That lets us serve models at scale. Basically, it's what it does. So in serving models, right, we have two parts in serving models. We have the prefill parts, and then we have the decode parts. And the thing with prefill is just what you need to understand about prefill is prefill requires lots of compute flops, right? It means you need a machine that is really, really powerful, that can churn through lots of numbers. And then you also have the decode parts, which doesn't really require you to perform lots of computations. But then what the decode parts or the decode phase requires is lots of memory. And the reason why decode requires lots of memory is because you need to load the model weights into either the VRAM or the HBM, depending on whatever like GPU you're making use of. And the reason why the decode part requires lots of memory is because it's sequential, right? So you have you it token predicts the next token basically. So maybe you're trying to ask what is what is your name, for instance. My name is Emmanuel. So is depends on my, right? And then is depends on name, excuse me, and then Emmanuel depend on its. Do you get? So each word within the sentence, each new word within the sentence depends on the previous word. So in order for us to like predict the next token, we need to be able to load all the weights of our model into our VRAM or into our HBM, and that's the reason why it's very, very memory intensive. But for prefill, we really don't need to load all. For prefill, we can like perform all of the computations in parallel in order to like sort of have the starting ground, right? From where the model can then perform the code. So you have the prefill and you have the decode. And what Dynamo basically tries to do is to make scaling these two phases independent. So you necessarily don't need to have all of the decode and prefill in one machine, right? You can have them in separate machines and scale them independently. But but doing that also comes with a bunch of things, right? So Dynamo helps you optimize those things that lets you scale your prefill and your decode loads independently. And one of them is smart routing of inference events, right? So you could have a case whereby some decode nodes, right? They have something called a KV cache. So see KV cache basically as like a database that tells you what your context is. By the way, is anyone familiar with what context means in AI and LLMs. Can anyone just maybe just give us a very, very brief description? All right. Yeah, Daniel.
Yeah. Context, from what I'm understanding is basically what the KV cache can see at once, what the model can see at once in a particular like window, like what. So like there's like the limit to what the model can see in I don't know that.
All right. Yeah, thanks. That's good, Daniel. So the context basically just defines, as Daniel said, what the model understands about a session. So if you're working with ChatGPT, for instance, and then you have like a conversation window, or you have like a conversation thread, right? The context basically is what is the memory of that conversation, right? And then KV cache is what is the actual substance, is the matter of that memory. So KV cache is what's is the building blocks of memory. It's what makes the memory. So what Dynamo helps you do is that these building blocks, these things that this matter of intelligence, which is your KV cache, it's usually very difficult to compute these things. Like it takes a whole lot of time. So and it sort of makes sense for us to always have to recompute the KV cache for our context all the time. So if we have a request that comes into our servers, right, and it's something that has been processed before by our system, Dynamo is able to immediately know, okay, this question has been processed by us. So we already have a KV cache, but because computing the KV values, rather, it's so expensive, I can just route this request to a node that has a KV cache already. That's one of the things Dynamo does. So we call it smart routing of inference events. And then there's also efficient resource management. And that's like the central theme behind Dynamo, which is we have the prefill, as I said, very compute intensive. Then we have the decode, very memory intensive. So we can efficiently manage the compute that we have, and we can efficiently manage the resource, the memory that we have, right? So Dynamo helps us like achieve a fine balance between managing our resources. So we have this is a high level architecture diagram of what Dynamo looks like. If you have access to previous slides, you'll probably have seen this diagram. I think this is also very instrumental towards understanding what Dynamo does, right? So you have user requests, right? Comes into the API server. API server is also like a component within Dynamo. And as you can see, we also have other components here. And usually the API server is an OpenAI compatible API. And you guys, if you remember, when OpenAI came, like they were the first in this industry. So they came with a standard of, okay, this is how you call our servers, or this is how you make requests to our backend, and everybody just sort of ran with it. So when Anthropic and Claude they came up, they just, you know what's the point of we having to change? Like, what's the point of we having to build another set of like another schema of how people communicate with our models when API is already the standard API? OpenAI, they were the first set of guys to do this. So it's just like a business decision that these AI companies made by following OpenAI's API standard, right? So the request comes into the smart router. Smart router basically is what tells us, okay, you know what, this is where the request should go to, or this is where should it go to the prefill, or should it go to the decode, right? And then we then have we then have a logical section here called disaggregated serving. In disaggregated serving, we have the prefill workers and we have the decode workers. Within the prefill worker, there's a prefill engine and there's also the decode engine. So these are just basically same as just normal servers as we know them. and they have their own KV cache, right? And that's the reason. And remember when we said that the smart router can route requests depending on which node has the KV cache that it needs, right? So the smart router is what basically does that. And then we have like the event plane. What event plane does is it's so all of these nodes, right? They all emit events that tells the system what the current state of Dynamo is. So if prefill worker isn't processing lots of prefill stuffs, like lots of prefill requests, then it's definitely going to send metrics to the event plane. I know what's I'm not processing enough. And what that basically means is that it's not doing enough work. And if it's not doing enough work, that's a problem. You're wasting your GPU hours, right? So the event plane knows that, and then it sends the events to the smart router, and the smart router is able to determine, okay, this preferred worker isn't processing enough of events. Let's send more events to preferred worker. So event plane just basically sends the metrics, and the smart router determines, okay, this is what we need to do. And we're going to talk more about the smart router as we go on, because it does a lot of really, really smart things when we want to, like it's really helps us, it gives us its sole capability to deploy our models to production in a way that reduces costs. And we have the Nixel NVIDIA Inference Transfer Engine. And what this basically does is it's the communication protocol that we use in communicating between prefill and decode. And the reason why is existing communication protocols, right? So Ethernet, as we know, isn't so fast with how, like it's not just so fast with how it communicates. The request usually in when we deal with Ethernet will have to like traverse from the NIC network interface card, right? Then an interrupt is called, which will trigger the kernel calls an interrupt, which will call your CPU. Then your CPU will have to handle that request, and then the packet travels down your Linux kernel before it gets written to socket. All of that is just so complicated, right? Before you know it, some milliseconds has gone, and that is not going to be so good to your users. So Nixel uses something called RDMA, remote data access, which lets you read directly from your network interface card, and your kernel really doesn't have to get involved in all of that. So it's always just have that at the back of your mind. And then we have low-level components. We'll start with the execution layer. In this case, what this basically means is there are certain components that like makes Dynamo, right? Dynamo. So if you look at how we deploy usually in production, for that usually it goes to Kubernetes. And for in Kubernetes, you have like different components that makes a Kubernetes. You have like control plane, right? And the control plane, basically what it does basically is it's determines, okay, this is how we handle the entire cluster, right? So worker nodes, and it's basically such capability basically extends to Dynamo, because that is Kubernetes. Sorry, Dynamo is deployed to Kubernetes. And one of the important low-level components within Dynamo is the GPU device plugin. Excuse me. And what this basically does is it treats GPU as resources. So think of how, I don't know if you guys are familiar with Kubernetes, but if you look at things like when you try to define your Kubernetes manifest for deployment, for instance, you want to like specify how much CPU should your Kubernetes make use of. You set requests and set limits. You could also like define how much memory should Kubernetes allocate to your workload. So memory and CPU are resources. When we deploy models to production using on Kubernetes, GPU is also a resource. So the GPU device plugin gives Dynamo, gives Kubernetes the ability to schedule resources, GPUs to our workload. So if you're saying, you know what, for this workload, I just want to assign a fraction of our GPU compute to this workload, you're able to do that with the help of GPU device plugin. So this is very, very central to scheduling workloads on production. And then we have the another part of low-level components we have is the inference engine. So I want you guys to see Dynamo this way. Dynamo is a distributed runtime, but Dynamo is built in such a way that it is very composable. The different parts that make up Dynamo, you could actually break them down and just use them independently of each other. So Nixel, as we talked about, which is a library that we use in communicating between nodes, you could just take that library and use it in a separate project, or you could just use that to communicate between your nodes without having to deploy Dynamo. Do you get? That's the way Dynamo is designed. And not only that, same philosophy also applies to inference engine. So in Dynamo, you're not like building your own inference engine from scratch. We make use of existing inference engines in the industry, and like we have very, very good inference engines. It's VLLM. By the way, does anyone know about inference engines? Like, what can anyone say about that? Is anyone familiar with SGLang, VLLM? Yeah, Daniel.
Yeah, so inference are used to run memory at scale. So all the GPU scheduling, the batching, they are owned by inference engines, right? So for low memory management because of the communicate with the GPUs basically. That was like VLLM is a popular inference engine. So yeah.
Yeah, thank you, Daniel. So basically, the main bottleneck about inferencing, because I was asked a question at the beginning of this, which is like, what's the direction of AI going into? I think inferencing is just going to be it, because think about it, as the usage of these models keeps increasing, as we keep finding more ways to make use of models, more applications, what that means is that inferencing will only just scale. Imagine we live in a world whereby we have like the best models possible. But having the best models possible just means you're going to train, right? Like you're doing a bunch of training in order to have weights that are able to solve problems in the best way possible, right? But then that's just one part. When we make use of those models, we need inferencing, and inference engines are like the central to that. And what they just basically do is that they perform the computation, the matrix multiplication that we know in attention, right? That is what inference engines basically do. The actual work that it takes to get your results or to get your answer from a question is what is performed within the inference engine. That is where the whole thing happens, right? But Dynamo sort of manages all of these components in such a way that they're able to work in tandem with each other. And the memory bottlenecks that we face when we are in the decode stage, right? We don't face it. If you just deployed your model without Dynamo, right, using maybe SGLang or VLLM, because you could actually deploy a model without Dynamo or by just using an inference engine, you would have to deal with all of these bottlenecks on your own. And that wouldn't be so good, because then it distracts you from solving your actual business problem, which is providing the best solution possible you can to your customers. So you don't want to deal with all of that. And VLLM uses there are a bunch of techniques that some of these inference engines have been able to use. We have page attention, we have predicts attention. So page basically just page attention basically is a technique. It's actually an operating system technique, right? That sort of mitigates or sort of handles how we allocate memory, because as we said, memory is very important, right? So page attention is basically how VLLM allocates memory to request, and same thing as SGLang also uses predicts attention, which is also another technique too. And then runtime execution, we have Torch, we have Coda, we have container toolkits. Coda basically, people like to see Coda as like a language. Well, yes, it's not just that. It's like the entire ecosystem that lets us communicate between our GPU and our CPU, right? So when we perform computations on our GPU, how do we synchronize, how do we write that data back to the CPU? CUDA provides all of that toolkits, right? The framework in order to perform that. So usually you don't even have to like write the work CUDA code that we know. There are a bunch of tools and like DSLs that have been developed, right? That we wouldn't even that can solve our problems, and we wouldn't even need to make use of code at all. And then there's also the container toolkit. When you deploy to Kubernetes, you need your containers, because containers are the center of Kubernetes. So your containers will need a way to communicate with your GPU drivers. The GPU drivers are those things are usually installed on the host. So the host is your computer, your machine, and then your container runs within your host. But then your container doesn't have a GPU on its own. The GPU is actually on the host. So in order to communicate with the GPUs on the host, you need container toolkits to do that. And there's also Nixel and Deco. We talked about Nixel earlier on. So then we have low-level components, right? For observability and control. There's something called NVIDIA SMI. I don't know if, can you guys see my screen? I'm on CMOX right now. I'm on the terminal. Can you see? Oh, you can see the terminal. Please let me know if you can see the terminal.
No.
Oh, okay. So what about now?
Yes.
All right, cool. So this is NVIDIA SMI, right? So it's basically I have a GPU instance, right? But within GPU instance, I have about 2 GPUs here. An NVIDIA GeForce RTX 560. So this is the first one, this is the second one. And NVIDIA SMI basically just gives you a high level understanding or representation of the current. Yeah. Huh? Hello?
Hi, Bash. How you doing? Good evening.
Yeah,
I
yeah.
wanted to ask, are you connected to a remote machine, or is it like the GPUs on your system?
Oh, this is a remote machine. I will get to
Okay,
that.
sorry, can I ask a follow-up question?
Okay.
Yeah, so are you connected to like a Dynamo instance, or you connected to what remote machine are you connected to, or what platform are you using to connect to it?
So this is Fast AI. Can you see this? So it's like it's a market.
Okay, thank you.
All
right, then. Yeah, we are starting.
How much is Gary Rubber?
Please can you
Ebube Chukwu, can you please mute your mic?
so
But could you take that again? I didn't get. Okay, sure.
Yeah. So to answer your question, okay, this is Vast AI. Vast AI basically is a marketplace where you can rent GPUs, right? You can come select whichever GPU, like you have data center level GPUs, A100, B200, even down to like this is the highest you can get, like B200s, right? And then you have the next H100 and the H200. And then you can come over to templates to select okay, which should be the image of your GPU instance. Do you want to just work off from NVIDIA CUDA, or do you just want like a barebone Ubuntu instance? So like when your GPU starts, this will be the this like be the foundation as which your GPU is strapped. So like in my own case,
Sorry, Mano. I mean, can we just continue and we can answer the question later? Okay.
Okay.
Didn't forget so that Emmanuel is able to cover everything he's supposed to cover.
All right, cool. All right, thanks. All right. So but we'll get to that anyway. So as I was saying, for NVIDIA SMI, we are just able to like know the current state of your GPUs, understand your GPU topology within the GPU topology within your computer. So in this case, I have about 2 GPUs here, and you can see the power usage. You can also see the temperature usage here, and I have like 2 nodes running. So there's a VLM worker, and there's a second one in GPU instance 1 and in GPU instance 2. So this is also one of the tools as you just sort of use to understand, okay, this is how your GPU is performing, and it's just one of those observability and control tools. And there's also one I didn't include here, but it's called NVIDIA Insights. Let's just move to deployment abstraction. So this is also something very interesting. We have, so when you deploy, I think, is anyone familiar with resources, Kubernetes resources? So we have things, is anyone, by the way, familiar, just quickly, is anyone familiar with Kubernetes resources? Well, so what a Kubernetes resource basically means is what says that's fundamental quantity that you actually deploy on Kubernetes. So if maybe you're deploying an application, you're deploying a Flask application, right? How does Kubernetes manage that Flask application, right? So Kubernetes does are using things called resources. And for LLMs or for deploying LLM workloads, we sort of like use a different kind of resource to do that. Because when Kubernetes was built, it wasn't built with a mindset of, you know what, we'll also be deploying LLM models or deploying AI applications, right? But when Dynamo came about, we also like had to deploy a resource that is like very tightly coupled with the requirements of today's AI applications, right? So Dynamo graph deployments it's just a declarative description of what the inference graph should look like. So inference graph is seen basically as when you make a deployment of your application, it consists of different components. So you could have like 10 prefill nodes, you could have like 20 decode nodes, and how do they all connect to each other? Representing that in Kubernetes, we use Dynamo graph deployments to do that. And then there's also like the Dynamo graph deployment requests. So instead of you specifying, okay, you know what, I want 20 prefills, I want 10 decodes, I want the requests, I want this prefill to use about 1 GPU, I want this other prefill to be assigned to the second GPU. Instead of you doing all of that, because in order for you to make use of Dynamo graph deployment, you need to actually know what you want. But for Dynamo graph deployment request, all you just need to do is to specify your SLA requirements. So what I mean by that is, okay, what kind of model are we deploying? And when you do that, Dynamo is able to, what is the latency? What is the throughput that we expected to provide to our users? Dynamo is able to just automatically determine, you know what, this is the number of prefills that we need, and these are the number of decodes that we need. And it's just going to like generate a manifest, a .yml file that you can easily just apply to a cluster and you set up the resources. So in one area, in the first one, graph deployments, you are specifying the actual values yourself and what you want your graphs to look like. But in graph deployments, you're just telling it, you're just writing basically English. Okay, these are the things I want, these are the specifications I want, and then come up with something that meets my needs. So then we can get back to this, but I just want to show you guys this diagram. All right, so this is the traditional serving, and we also have the disaggregated serving. For traditional, as you can see, we have a compute, which is a prefill. As we said, it's very compute intensive, and we have our memory, which is decode in one machine, right? And when you have them in one machine, memory compute might be struggling for resources in order for it to like compute more KV values. But then the memory guy, the decode is actually doing some other stuff, which will starve the prefill node of resources. So in the segregated serving, we're just, and I'm actually going to show you guys these two things. So in segregated serving, you can see that we split our request into 2 nodes. So we have the prefill, dedicated GPUs to improve prefill efficiency. And as we compute KV cache in our prefill, we send those KV cache to decode using what? Does anyone remember? Using Nixel. So Nixel is a communication library that we're using, moving KV cache values from prefill into decode. And then decode can then start performing its own job, right? Which is generating the actual output. And there are two metrics that we really care about when it comes to model 7. The first metric we care about is the time to first token. So time to first token means what is the amount of time that is to take us to generate the first token within prefill. If it's taking us a long time to generate the first token within prefill stage, it means the latency is so high and our users won't be happy. And then we also have on the second metric that we care about is ITL, inter-token latency. What that basically means is how much time does it take to output a token after the previous one, right? So if you have two tokens being outputted in the decode phase, what is the gap between those two tokens? And you can, when you make use of ChatGPT and stuff and Claude and the rest, you can notice that sometimes when it outputs a token and it takes very long while for it to output the next token. We don't want to do that. So we want to be able to have our models output tokens as quick as possible. So I'm going to show you guys. So for aggregated 7, I made a video, I made a screen recording, and the reason why I did it was and the reason I made a video for this, but for the order, I'm just going to show you guys how. I'll show you directly from the terminal. Okay, yeah. So on this left-hand side, so I have about 4 pins there on CMOS. On left-hand side is just like what we basically do here is just to forward the requests from the terminal into our front end. So they're like two important components to us here in Dynamo. There's a front end. The front end is just the guy that houses the OpenAI specification. It has the endpoints that we call things like create charts, chart completion, and stuff like that, right? And then there's also the backend. So the backend is to the right-hand side. This is the backend, right? And on the bottom here is NVIDIA SMI. So you're going to notice that when I send a request, let's play. So at the bottom here, so when I send a request, if you notice, can you notice the utilization? It goes up, like it shoots up to show you that we perform our prefill and our decode in one node. So to make the point clear again, for aggregated 7, which is what I'm demonstrating right now, prefill and decode happens in one node, right? And to the right-hand side, this is where the prefill and decode happens. So if I click on play again, notice when we send a request, the utilization increases 82%. So this is performing 2 things, prefill and decode, right? And but in this case, this is going to be a problem if we are sending lots of requests that have very large inputs. Then it's going to take a very long while for the prefill phase to complete. Because imagine sending like the whole of Harry Potter, for instance. Let's hypothetically, let's say you send the whole of Harry Potter to the model to ask questions about it. Prefill is going to be very, very long. It's going to take a very, very long amount of time. And what that basically means is that other users are trying to send in their requests. Their request won't be attended to because the prefill node is already computing the previous request, which is to process the whole and Harry Potter text, right? So what we want to do in this case is, so first of all, split prefill and decode. So the prefill node can handle prefill, decode node handles prefill. And not only that, we also want to like reduce the amount of requests that we send. So instead of like just sending the entire set of Harry Potter, we could like batch it into small components. So rather than processing the whole thing, we just maybe process a bunch of tokens, and that's way, as we process one token, right, we send it to the decode, and the decode completes it, rather than processing the whole hypertext and then sending it to decode. That won't be good. So continuous batching is also one of the techniques that we use in optimizing um optimizing inferencing. So this is the diagram for disaggregated 7. We have a client here, we have the decode worker, and we have the prefill worker. So a request comes in, we check for prefill availability. So the top section here is for when prefill workers are available. So if we have a prefill worker available, we will just forward that request to the prefill worker. But if the prefill worker isn't available, right, the decode worker will perform both prefill and decode, right? So let's just stick on when there's a prefill worker. We compute the KV cache. As soon as we are done computing that, we send the request back to the decode. As you can see, we use Nixel to do that. After sending the request, we then generate tokens, and sequence continues that way. So if to illustrate using the example of Harry Potter, if we are sending batches of a text, we don't have to process the whole sequence of inputs. We could just batch it into small bits, and as soon as the first batch is done, we send it to decode, rather than having to wait for the whole batch to be complete. So we'll just have like a demonstration of disaggregated 7 here to show you what we're really talking about. So, okay, all right. So I already have everything set up. So on the bottom parts here, let's do this. So what we have one is where we'll be sending our requests, right? So we'll just let's call this. So we'll just, yep, okay. So we'll just call coil. Coil will be what we'll use in like interacting with our with Dynamo. And then at the top here is the front end. At the top here is the front end. And at the right here, we have like 2 panes within the right. So we have 2 and we have 3. So the top one is prefill. So the top one is decode, while the bottom is prefill. And on the right here, which is the 4th pane, is NVIDIA SMI. So let's show you this. And as you can see again, we have 2 GPUs. But in this case, we already scheduled our prefill and our decode on each of these GPUs, rather than having all of them on one GPU. That's why you can see the utilization. For each GPU, we have about 16 gig of memory in our GPU. But if you look at here, but if you look at the example for aggregated 7, everything is scheduled on one GPU. So you can see we've used 14 gig out of 16 gig for aggregated 7 on GPU 1, on GPU 0. But on GPU 1, we practically didn't use anything. And then if you check processes, we only have one worker, which has both prefill and decode. Unlike in disaggregated 7, where we have prefill on one node and we have decode on one node, and then you can also confirm it within the processes section. Right. So one thing I'm going to do right would be to send a request. Right. So as you can see, on both sides, on both sides, on the prefill and on the decode, you can see they both listen to the requests. And you can, if you notice, look at our utilization on NVIDIA SMI. You can see that these both values do change, which is the request comes to the request comes to both our prefill and our decode nodes. Right. Then one thing I want to show you is if we terminate our prefill node, the decode node will also like handle the request. But if we terminate the prefill, nothing will happen. So let me show you Let's terminate one. We show, so this is our prefill, which I'm terminating. Right. So now that we've terminated a prefill node, okay, we've terminated a prefill node. Let's then make a request. Yeah, we still get an answer, right? So what we asked was, what's the capital of France? And the decode is able to respond. And this is, we can say NVIDIA SMI. But then let's then Q3. All right. So, but then let's start up our prefill back and let's terminate decode. So we are terminating the decode node, and in this case, we won't be able to do anything because we will always need, usually in Dynamo will always need a decode node. The decode node is always like the fallback node. When there is no prefill, the decode will act as prefill and decode. So as you can see the value for the decode for prefill changes, but nothing for decode changes, and we don't even get any response from coil. So so we start this back up and everything should go back to normal. So Q1. All right. We'll have to like wait a bit for the prefill for the decode nodes to come back up. So yeah, that's so the point basically of the disaggregated 7 is we're just able to split requests into 2 nodes, and because we don't want one node to be bottlenecked by the other, right? That's what we do with that. And then let's look at what Dynamo also enables. GPU scheduling. There's something called topology awareness, and what that basically means, I'm just going to like run through this, is that when we have issues on a cluster, right? One thing we really care about in model 7 is latency. We don't want to be able to, we want the response of our request to get back to our users as quick as possible. But if for any reason a node within our GPU cluster or within our cluster goes down, how do we schedule that node back up? So imagine having 2 prefill nodes and having 2 decode nodes, and one prefill goes down. Ideally, would you want to schedule that? Would you want to bring up a new prefill node that is in a place very far from where your existing nodes are? If you do that, it means you're increasing latency. So what GPU topology awareness does is that when a node goes down, NVIDIA Grove will try to figure out, okay, is there any existing node that is very close to the 3 other nodes that we have, which is the 2 other decode and the 1 prefill that we have, and then it schedules it together all in one place. Usually it's going to be maybe within one GPU rack. So there's something called NVL72, which basically just is how like these hyperscalers usually deploy their models. So in essence, we want, when our nodes go down, we always want to schedule our decode and our prefill nodes to be very, very close to each other. That's the essence of topology awareness. And then there's also the inter-GPU data transfer that we talked about, which is how we communicate between prefill and decode. And KV aware routing, I think we've both touched on that. There's also the production deployments where we use AI configurator. And what this basically means is when you want to deploy your models, you wouldn't just want to do that blindly. You want to like have a bunch of values, like have a feel of, okay, what are the resources that I need in order to deploy my models? And what you can do is AI configurator. AI configurator basically just lets you you set a bunch of values to the CLI command, right? Like model type, ISL, and TTFT, which we've talked about before. And then it will come up with a YAML that basically says, you know what, this is the optimal configuration that you need in order to set up your cluster for serving models. And that's what's and and that's what basically it does for you, right? AI configurator. And there's also the Dynamo graph deployment request. We talked about this earlier on. In this case, this behind the scenes makes use of AI configurator, right? AI configurator is a standalone tool on its own, but Dynamo graph deployment request makes use of AI configurator. I know we talked about this earlier on. All you just need to do is, in this case, you Dynamo DGDR is actually a request. It's actually a resource on its own. So you can like declaratively outline what your requirements are, performance constraints, hardware assumptions, backend choice, what kind of inference engine do you want to make use of, what kind of model do you want to make use of. You define them within your .yaml file, and Dynamo um, does everything for you, as against just using a CLI command, and you then have to like copy the YAML file and apply it on your own. This just does the whole thing for you automatically. So one very interesting thing, which is my last slide here, I also want to talk about is fault tolerance when it comes to deploying models. I know like when you, so for some of you guys, when you make use of models, right, and like you send a question, like you could start reading the answer and you might not be able to, like, you might not like it, what you're seeing, and then you just like terminate the output. But if you terminate the output, then how are we sure that all that our nodes have also terminated that output? Because if we don't terminate it, it means we're basically wasting money. Imagine asking a model a very, very long question that takes about 10 minutes for it to respond to you, right? Once you terminate such requests, it wouldn't make sense for your nodes to keep on churning KB cache, right? So one thing that Dynamo really does for us is that it lets us deterministically stop computation of cancel requests. So you are very sure that once a request is canceled by your users, your nodes are not performing extra computations or extra work that is not needed. So that will be it. If there's any question, I would appreciate.
Thank you so much. There is a question already. And then, I mean, if you have questions, please raise up your hand or you can drop it on the chat. I think Samuel has 2 questions for you.
Okay.
Sure.
Okay. I just wanted to ask concerning Dynamo. Can it be used on a single CPU connected to cloud GPU? You would need GPUs to do this, right? So Dynamo has like a bunch of components. It depends on how you choose to deploy. The front end really doesn't require a GPU, right? And there are ways you can, like if you go through Dynamo, you could see that there are components that require GPUs and components that don't require GPU. I could maybe just show you a YAML file where we outline, okay, this is our front end and this is our prefill node and this is our decode. So you could schedule, to answer your question, right? You could schedule the front end. Remember, the front end is what houses the OpenAI specification. That could be scheduled on a machine that is CPU based, right? And then your prefill and your decode will be on a machine that is GPU based. And your other components like NATs, right, could be on a machine that is CPU based, because we don't need GPU for that. What we use NATs for in Kubernetes is for us to like just communicate commands between the components. So there are 2 things. You use NAT to communicate commands between your components, and then you make use of Nixel to communicate inference requests. And the second question, what else is the difference between Dynamo and Nemo? And does Dynamo have to be only for billion? No. It doesn't have to be for. You could save any model with Dynamo. It could, like what I just said right now. It's a 0.6B 600 million para model, but usually to get the best, most people who use Dynamo on a very large scale are folks who are like 7 millions and millions of requests. But now you don't have to. It doesn't have to be a billion parameters model. Yes, OBG, fine.
Okay,
Hello?
good evening. Hello, can you hear me?
Yes, sir.
Okay,
I can hear you.
All right, thank you so much for this wonderful presentation. I really so much enjoyed it. But my question there is that for we, or let me say I myself, that is a beginner, how will I start? Because I'm so much interested to learn machine learning. So how will I start? How can I be mentored? Because actually going through it on this presentation, I understand some actually, and there are some terms I did not actually understand, which you also need a kind of one-on-one mentorship, maybe due to if I'm being guided on how to start with. I will be so much appreciated on that. So for the beginner like I myself, how will I start, sir? Thank
All
you.
right. Thank you so much for the question. I think if anyone would you want to, if anyone is she's the coordinator of this great events and learning group. So I think if anyone really wants to take a stab on that.
Thank you so much, Emmanuel. Fiona is had to jump off
Oh, okay.
to attend to something else. But again, Mr. Ifeanyi, like we shared before last session, that we usually have our study group cohorts. Which one is currently running, where it is majorly for beginner, that is machine learning and generative AI. So, I mean, if you've missed, of course, you cannot join just yet, but very soon, another study group is going to come up, and then you can join to start your journey. We will, since you're in the community, you're going to see the information. Just join, and then you can begin your journey with that. I hope that answers your question, Mr. Ifeanyi.
Yes, thank you so much. I appreciate.
All right, thank you so much. Does any other person have a question?
Somebody asked about fast AI. I don't know my answer to that. Like I was already even good on the tangents while I was answering that, but was my explanation good enough for you? I don't know. I can't remember who asked it. Was it Ifeanyi? No, not Ifeanyi.
No, it was. I think it was Ope or
Wait,
something.
okay, yeah. It was Ope. Is Ope still here? I don't think so. So
Does anyone have any other person have questions for Manuel? That was such a full session. All right, Manuel. I mean, in the absence of question, I mean, maybe people will drop their questions in the group, and we would share with you. Thank you so much.
all right, thank you very much.
Are you? I mean, because I know that a lot of people always ask for the slide. We
Okay.
just share the slide with the email.
All right, okay.
On the email trail that I've been exchanging, and we will share with the community with the recorded version. Thank you so much. If you would please stop sharing so that I can continue sharing my screen. Thank you so much. We're so that was such
Thanks.
a rich session. Thank
Thanks
you.
for having me.
Okay, so yeah, thank you. Since there are no questions anymore, please follow us on X and on LinkedIn, so that we can, of course, if you're in the community already, you're going to get updates, but just follow us and share with your friends to follow on social media. Our upcoming event is the February technical session and office hour. Like I said earlier, you do not want to miss any session in this year, because we are cooking a lot of things for you. And we're also working on the feedback that we've been getting to improve the sessions. Also, if you have feedbacks, I just encourage you to please share your feedback. I'm just going to share this now in the chat just in case. I mean, it's usually better when people share their feedback while they are still on the call. You can just share your feedback, let us know how to serve the community better so that we all can get the full benefits of the community. Once again, thank you so much, Emmanuel, and thank you for everyone who took our time to join us. Without you guys, this sessions will not be as awesome as they are supposed to be. And then we appreciate you guys for always joining. And then we also appreciate all of our guests. Thank you so much, Emmanuel. That was such a rich session. We hope to do more with you in the community. And we hope that you eventually become a part of the community. Thank
Sure,
you.
there's nothing here. Thanks for having me.
Yeah. So in the absence of no question, I would say thank you, everybody, again. And then till February, we'll look forward to many more of this year. All right, Manuel, good night. Thank you.
Yeah,
And
bye.
everyone, good night. Bye.